Go ahead.
Yes, good day. Good day, everybody. This is our Stochastic Programming Seminar Series. Today we have our junior session with two young but very promising researchers. And so this is our second such type of event. The previous one was during the fall, was during the springtime. Now we are in the fall, and we will have our last seminar in this series, in 2 weeks' time. So today, however, we are pleased to introduce two presentations, 25 minutes each, by Dr. Zhang. He graduated from his PhD at University of Southern California, working under the supervision of our most esteemed colleague, Surajit Sen. And he was previously he's currently working as a scientist at Amazon. And then he was previously, so he had his bachelor degree at Columbia University in operations research. So welcome. So today, as you can see, he will be presenting a sampling-based progressive hedging algorithm. His particular interest is in numerical methods and approximation methods for fast convergence of large-scale stochastic programming. And then after we will have Bianca Marin Moreno, originally from Brazil, but then I will be introducing her. So Dee, thanks for giving this presentation. I leave time to you.
Yeah, thank you. So let me begin my topic. Yeah, so today I'm going to talk about a method to solve stochastic programming. It is a variation of progressive hedging algorithm proposed by Rockefeller and Watts. This is a work with my advisor, Professor Sen, and another PhD student, Yihang Zhang. We are from University of Southern California Industry and System Engineering Department. Before I begin my talk, I want to do some advertisement of my work. So basically, I mainly focus on this work and a few other works during my PhD, but they are very related. If you take a look at what I have done before, you can see that my work is quite related, and it is like a full story, and which lead to this sampling-based progress hedging algorithm for stochastic programming. So I think it's worth for us to take about 20 to 30 minutes to listen to someone who has been working for about 5 years in this topic. And if you feel interested in this work, please feel free to, if you Google this title on the Google search, you can find the specific paper. And if you feel interested in this paper, please feel free to set this paper. And I think it's very important for some young scholars like me. Yeah. So let me begin my talk. Let me begin my talk by setting up the background of this problem. So we try to minimize the function fx, which contains two parts. The first part is a convex function, and the second part is an expectation of a random function, hx omega tilde. It can be non-smooth. And for classic progress hedging algorithm, we will have some assumptions. The first one is omega tilde should be discrete. It has finitely many realizations, and finally, its probability distribution should be given. And with these assumptions, we can reformulate fx as a sum of ps cx plus hx omega s. With these assumptions and problem setup, Rockefeller and Watts has come up with this classic progress hedging algorithm, which is very similar to, it shares the similar ideas as in the ADMM method. Basically, we have a primal and dual update. In the primal step, we will solve this augmented Lagrangian function and get the scenario optimal solution in each scenario. And because of this non-anticipativity constraint, we are going to have a sort of a weighted average of all the scenario optimal solutions to get this X bar as our feasible primal solution. And once we get the primal solution, we are going to use a gradient-based update rule to update the dual variables. Basically, if you take the gradient with respect to lambda s in the above augmented Lagrange function, you can find out that the gradient is actually xs minus x bar. And here we also take the step size as the penalty parameter rho to update the dual variables. This is the very classic progress hedging algorithm. It has many applications in different areas, like in the power system, in inventory control and finance. But it still have some limitations which motivate us to think about some modifications of this work. So let me begin the topic by giving you some motivations, propose some limitations or questions about the classic framework. So the first question is how to handle the situation where the distribution of omega tilde is unknown. Very intuitively, we can basically use simple average approximation to solve the problem. But by what I mean is like here we first sample S number of scenarios and formulate this f hat x. And if size of S is large enough, then we can say that by solving this f hat x, we approximately solve the original function fx. But the question is how to choose the sample size S so that the function approximation f hat x is close enough to the original function fx, the expectation version. This is a tricky question. And the second question is how to generalize the deterministic progress hedging algorithm to a stochastic version. Here I say the classic framework is a deterministic version because once you sample a large collection of scenarios, you never generate more scenarios for a classic progress hedging algorithm. And in that sense, it is very similar to the ADMM deterministic method. Just like we have a gradient descent method to solve deterministic programming problems, we want to use a stochastic gradient descent method to solve stochastic programming problems. So we want a stochastic extension of this deterministic progress hedging algorithm. There are some pioneers which try to do so. For example, here I have one of them. It is called randomized progress hedging algorithm, which the authors use to solve the multi-stage stochastic programming. But the drawback is like they still generate a large number of scenarios at the very beginning. And then at each iteration of the algorithm, they will sample a subset of scenarios. So it is between the stochastic and deterministic, but it is not really like a fully stochastic version. So it cannot allow more scenarios as we needed. Our approach instead will use an adaptive sampling framework, where in each iteration we generate size of sk scenarios to make sure that our function approximation f hat k is close enough to the original function fx in a very small region in a ball among the current decision variable xk. We will try to find a guidance of how to choose the size of SK using concentration inequality and sample complexity analysis. We are going to talk about later. The third question is how to update the dual variables. The current method is to use a gradient-based method like we have discussed earlier. But it is only accurate, this gradient is only accurate at the current point, and we want to find a better direction which could potentially accelerate the convergence without adding too much computational burden. The first thing I want to say here is like, we cannot use second order method because we usually, as I said, when I set up the problem, it can be a non-smooth problem, so we may not have the second order information. Also, even if we can, mimic the smooth case to get some second order information, maintaining a sort of a Hessian matrix is very tricky for large scale problems. So instead, we are going to use this stochastic conjugate subgradient direction. which we will talk about later. The last question is, the convergence rate of the classic progress hedging algorithm is highly sensitive to the choice of the penalty parameter. There are a lot of literatures which try to adjust the penalty parameter role to have good practical performance for the algorithm, but most of them are computational experimentation method. Here we will propose a new method which is more mathematically motivated, and which also adheres to the principle of optimization. Here, to be more specific, we are going to use a line search method to make sure that the dual objective function value have sufficient increase, and because it is in the dual space, and also the directional derivative have sufficient decrease. So with all of these motivations, let me set up the goal of my project. We will have two frameworks. The first one is the classic progress hedging algorithm proposed by Rockefeller and Weiss, and the second part is an adaptive sampling framework. It is actually a previous work with my advisor, and it is under review by SAM Journal of Optimization. It is very close to be published. We only have to make a very small minor review. Using this new framework, we want to handle some of the difficulties or like limitations in this classic progress hedging algorithm. Specifically, we want to have some guidance of how to choose the scenario size using sample complexity analysis. We want to use conjugate subgradient direction instead of gradient direction to update the dual variables. Also, we want to find a adaptive strategy to update the penalty parameter to make sure we have good practical performance. And with all of this, it comes the sampling-based progress hedging algorithm. So I'm going to first do some introduction about this adaptive sampling framework because it is a very important part of our algorithm. So this adaptive sampling framework, also called stochastic conjugate subgradient algorithm, because the major component is using this conjugate subgradient direction, has three major steps. The first one is still using adaptive sampling to have a good stochastic function approximation. Here, the size of Sk will be determined by some sample complexity analysis, using some concentration equality to make sure that Fkx will be close enough to the original function Fx in a very small region among the current decision variable Xk. And the next step is to use this non-smooth stochastic conjugate subgradient direction. The direction is obtained as follows. First of all, we get a subgradient in the subdifferential side at xk, and then the new direction dk will be a convex combination of the previous direction dk minus 1 and the current subgradient gk. This new direction will have the smallest norm in the convex hull formulated by dk minus 1 and gk. There are many good properties of this direction I'm going to talk about in the next slides. And the last step is to choose a good step size, probably using Wolff's line search to make sure that we satisfy this strong Wolff condition in the non-smooth case. Note that L condition makes sure that since now we are in the primal space, so L condition makes sure that the objective function value have sufficient decrease and the directional derivative has sufficient increase. Let me give you some motivations about why we want to use this conjugate subgradient direction. I'm going to compare the conjugate subgradient direction with the heavy ball momentum method. So here, the first theorem tells us that if we keep using this conjugate subgradient direction, then the direction dk, the opposite direction of dk, is actually a convex combination of all the previous subgradient, and also the norm of dk converges to 0 as k goes to infinity. And if you take a look at the heavy ball method proposed by Polyak in 1964, you can, after some mathematically reorganization, you can find out that the direction in the heavy ball method is also a convex combination of all the previous gradients. But there are two differences between our method and the heavy ball momentum method. The first one is that the heavy ball method, if you want to have some convergence property, it can only be applied in the smooth case, but our method can be applied in the non-smooth case, and also the weight before this subgradient is different. So you can think about this non-smooth conjugate subgradient method as a like an extension of the heavy ball method to the non-smooth case. We also have some convergence properties of this method, but I'm not going to mention it here because of the limited time. Now I'm going to show you an example about how to use this method to solve some real-world stochastic optimization problems. The example I use here is kernelized SVM. It is a very special case of a two-stage stochastic programming problem without constraints. And I'm going to compare three different algorithms. The first one is called Wolf. It is a deterministic conjugate subgradient algorithm proposed by Wolf in 1975. It can only be applied for small data sets because it is basically an all-in-one problem, all-in-one setup, and if you apply it to large-scale problems, it will take it forever to finish the algorithm. The second algorithm is called Pegasus algorithm. It is a stochastic first-order method. This method has can be applied for large-scale problems, but compared with our adaptive sampling framework, the performance of our algorithm is better, both in accuracy and time. So you can see that our algorithm is very powerful for solving some stochastic programming problems. Especially you can take a look at this side and you can find out our algorithm has very good performance for large-scale data set. Now let me give you some high-level ideas of this sampling-based progress hedging algorithm. First of all, you can think about it as a combination of classic progress hedging with the adaptive sampling framework or the SCS algorithm. In the primal update, when we want to update the primal variable, we are going to use the classic progress hedging algorithm, basically formulate the augmented Lagrangian function, and then take the average among the scenario optimal solution. But for the dual update, we are not going to use the gradient descent method Instead, we are going to first formulate this dual objective function LK lambda, and then use this dual objective function as the objective function in the SCS algorithm, and then use the SCS update rule to update the dual variables. It is very similar. Another understanding is that it is very similar to the ADMI method, but in the dual update, we are not going to use gradient descent method. We are going to use SCS method to update the dual variable. So let me summarize the major steps of this new algorithm. First step is still do an adaptive scenario sampling, and this size of SK will be again be determined by some sample complexity analysis. Then the next step is to update the primal variables. We will still formulate the augmented Lagrangian function, and then solve the scenario get the scenario optimal solution, and then take the average among those solutions. And the next step is to use this conjugate subgradient direction. It is a convex combination of the previous direction, dk-1, and the current subgradient gk. Here, the subgradient or the gradient is basically xks minus xk bar. And once we get the direction, we will also formulate the dual objective function. And we will search along the direction dk to and find a good step size, which makes sure that the objective function, the dual objective function, have sufficient increase for the objective value and also have sufficient decrease of the directional derivative. we can, there are actually some theorem which guarantee that such theta exist. Okay, so now I'm going to talk about some convergence analysis of this method. First of all, as I have promised you earlier, I'm going to give you a guidance of how to choose the scenario size in each iteration. Here I define two functions. The first function is like a simple average version of the dual objective value, and the second function L is the expectation version of the dual objective function. And the theorem here tells us that if with sample size of sk greater than or equal to the right-hand side value, then we can make sure that with high probability in a small ball among the dual decision variable, we can make sure that our simple average approximation will be close enough to the original function L in a small region with high probability. Yeah. So there are two ways to show the convergence rate of our algorithm. The first way is to use the contraction method, similarly as in the classic progress hedging algorithm, but we will only show it in the dual space. The primal space will, in the primal space, it will be very straightforward later. But here I'm going to only mention the dual, the contraction mapping in the dual space. First of all, we are going to have this theorem. It is like a here it is a sub-martingale theorem. Basically, we define a function which is the difference between Lk plus 1, the dual variable in the k plus 1th iteration, and the dual objective function Lk in the kth iteration. And we can say that the difference between them is greater than theta epsilon delta k, which means that it is a sub-martingale property. Also, you can think about it as a sufficient increase property in expectation. And just like similarly in the deterministic optimization world, when we have sufficient increase for the objective function value, we usually can show some contraction properties of the decision variable. Here, since we are in a stochastic setting, we can only show that the dual decision variable sequence will be a contraction in expectation. So we will add an expectation just like it is a very standard extension to the stochastic world. This is the first approach to, and after you getting this contraction mapping, you can definitely show some convergence rate of this algorithm. This is the first way to show the convergence rate. The second way is to use the renewal reward theorem. Basically, we first define a stopping time t epsilon, which is the first time that norm of dk is less than or equal to epsilon. And with some standard assumptions, we can show that expectation of t epsilon will be bounded by O of 1 over epsilon square. In the right hand side, here is the 1 over epsilon square comes from. So we can say that the convergence rate of such algorithm is actually 1 of 1 over epsilon square. But if you use this this version, the contraction mapping version, you probably can have a better convergence rate. This is something I'm still trying to figure it out, but I just want to mention it here. At least we can get O of 1 over epsilon square. This is already the I think the best convergence rate for non-smooth problems. And also we can show the optimality condition. If we have norm of dk less than or equal to epsilon, then we can show that the solution we get xk bar, the objective function value fxk bar, and the optimal objective function value fx star will be bounded by O of epsilon as well. So this is some convergence analysis. Finally, I'm going to use some illustrative experimental result to give you some feelings about the advantage of this method. So we will compare 4 different algorithms. The first one is classic progress hedging algorithm, and the second one is randomized progress hedging, as I have mentioned in the literature review part. And the third one is our sampling-based progress hedging. Last one is called stochastic decomposition. proposed by my advisor. I'm pretty sure that everyone here knows this algorithm. Yeah. So we can say that for especially for large data set, our method performs better than the other method. Basically, it converges faster. It performs relatively close in the end, but it converges faster. There are two major reasons, I believe. The first one is that for sampling-based progress hedging algorithm, we can sample a relatively small scenario set at the very beginning and to get a relatively good solution. But later we may add more scenarios as we need it. But for classic progress hedging or randomized progress hedging, we have to solve a very large scale scenario subproblems even at the beginning of the algorithm, because we cannot add more scenarios and we cannot use a very small data set at the very beginning. So we have to solve a very large scenario subproblems even at the beginning, and that basically wastes a lot of computational resource at the beginning. And the second reason is basically we use the conjugate subgradient direction instead of the gradient direction, because the conjugate subgradient direction is like a momentum method, which accelerates the convergence of the algorithm. So we definitely can converge faster than the gradient-based method. Yeah, these are two advantages of these are the two reasons which cause the method to outperform other classic framework. Finally, I want to give you some summation of my work. First, we have come up with this new approach, new sampling-based progress hedging algorithm for large-scale stochastic optimization problems. And compare with the classic progress hedging algorithm, our method does not need to know the explicit form of the distribution of the random variables omega tilde. It also allows adaptive update of the sample size, where we use the concentration inequality and sample complexity analysis to find a good sample size SK. And lastly, the update of the progress hedging parameter, penalty parameter rho adheres to the principle of optimization. Basically, we use a line search method to find a good step size, which satisfies the sufficient increase of the dual objective function value and the sufficient decrease of the directional derivative. And lastly, we have used some illustrative experimental result to show that our algorithm has good performance in practice. That's the end of my talk. Thanks so much for your listening. If you have any questions, feel free to ask. Yeah.
Thank you, Dee, for this